Can you see my slide?
Yeah, yes, sir.
Okay.
Yes.
So yeah, the last session, the topic, I think we spent quite a bit time talking about the microwave, the chemical looping. All right. So basically, we select two material, iron as a chemical looping the carrier, and then under microwave we run 3 cycles, and then the microwave is always better. Okay, the good question asked was, hey, why the for iron and also for the shape are different? Wow, that's a very good question, because keep in mind that the shrinking core model, the structure of the chemical looping agent keep on changing. All right, the more peaks, the more difficult, because if you have ammonia come out in a single peak, I mean it's easy, but sometimes it's very difficult to react nitrite with hydrogen in the bulk, and then the dissolved ammonia. So that's why sometimes you have multiple peaks.
Wow.
We also talk about the differences between iron and the and the cobalt moly. So basically the cobalt moly, you first cycle actually it appear to be very good, and later on the activity diminution. Okay, so now the next slide I'm going to talk about what's the reason cause of this. First, we have to understand the so-called active site the structure. Active site structure means if you the cartoon, what's the in here? If you draw the structure here, so in the bulk region, what's the look at this circle. What's the microstructure in here? I mean, I I think in the paper they use the so-called the particles represent the item, but in reality they are bonded, they are connected. Okay, so this black dot, which is nitrogen, and then they are connected to the manganese. Or in our case, in other case, they connect to the cobalt moly. How nitrogen are the bonded with cobalt moly to begin with, because you have to activate the nitrogen. It's called nitridation. And then to begin with, what's the structure? So-called active phase. And then that active phase will react with hydrogen to become the ammonia. Okay, it's important to understand what's the active phase. It means cobalt moly react with N2 to form nitride. So there's a technique called the very simple called XRD. Anybody understand XRD stand for?
Yes.
What's XRD?
Yes.
X-ray diffraction. Okay, X-ray diffraction is I mean, if you go to you go to see doctor, you see the X-ray, but that's basically scan your human body, all right, to see your bone and something. Same thing with the material. XRD diffraction is going to see the material, but it's more intensity much higher than the XRD, the medical XRD. Okay, so basically they can see the material, the active phase. So let me interpret this graph. So this graph means first we take a cobalt moly. Remember the cat is cobalt moly. We take XRD. So on the bottom is blue. The spectral is cobalt moly. Then we purchase a standard material. It's cobalt moly and a nitride. You can buy this material. We want to see, hey, if you have the complex which has 2 cobalt molecule and 3 moly, and then bonded with nitride, how is the XRD look like? Yeah, well, this XRD look like diffraction. Okay, so then we move on and then to see how the what do you call that CO3, MO3, the nitride look like. Okay, so every time we go up, we see the the circle standard the process. So 1, 2, 3. So keep in mind watch this structure. I'm going to draw a circle here. Okay. All right, I'm gonna move this. Oh, I'm gonna move this circle around. Cobalt moly. Look at this circle region. Okay, and then the second standard, the third standard. Okay, look at this region. So this is the cobalt 3, moly 3, and nitride. It's cobalt 2, moly 3, nitride. It's cobalt moly, no nitride. Now, when we go to the so-called after 3 cycles, the spent catalyst, look at the circle. Okay, so the basic spent catalyst still contains the so-called active phase. That means we are not fully depleted the nitride. It still contains nitride in there. So now I'm going to enlarge. Did you see something here? So basically, spent catalyst has the peak like this, and also the standard we bought has some peak like this. So what does that mean? That means during the reaction for the spent catalyst, there's active structure like this. Okay, keep in mind that this is cobalt moly 3 is the standard we purchased, but the material after the 3 cycles, they have similar peaks. So what does it mean? That means make sense? All right. So look at it. This is standard. Okay. So this is standard we purchase. And then this is the spent catalyst. Okay. So that means during the reaction, there's a phase. Even if you begin with cobalt moly, and then during the reaction, they form the phase just like this. So the information from XRD is help you how you design the cobalt moly catalyst. We probably will not start from cobalt moly. We probably will start the cobalt 3 moly 3 because that's active phase. It's already formed the structure because based on the XRD analysis, we do see the so-called cobalt 3 moly 3 the structure which is similar to this. So that means it's active phase. So what does it mean? That means you want to build a material, I mean, not from the scratch. Cobalt moly is built from scratch. True. When you react 3 cycles from cobalt moly, you will see this structure. What if you bypass cobalt moly? You start from cobalt 3 moly 3. It's much faster, all right? So that's the whole idea of how you design the material. You have to understand the structure. What is the active structure you need? Then you design and try to get close enough rather than start from cobalt moly. But unfortunately, we learn this, the after fact. We learn this after the 3 cycles. We take sample here. At the beginning, we didn't know, so we begin with the cobalt moly, and then we come to here, and then we learn, it's a cobalt 3 moly 3 is active phase. So in the next step, we are not going to start from cobalt moly. We are going to do active phase. So hopefully we will solve this the problem because this material they are not stable because of the structure that keep on collapsing. Any question on the XRD to identify the active phase? You understand here? You have to calibrate. Yeah, go ahead. You understand? Any question?
Yeah, yes, sir. We understand, sir.
Okay, cool. All right. Now, this is the last part of the lecture today. And then tomorrow we are going to move to the low pressure separation and economics because they tie each other. So economic analysis, if you use the unconventional, let's say microwave or the plasma, you lower the pressure, or you chemical looping, your lower pressure, your back end separation cannot be cryogenic, so has to be the the technology like a solvent or the pressure swing or membrane. So that tie with the economics. So that will be tomorrow. But today I really need to finish this the plasma chemical looping. Okay, so I think I showed you this before in the general overview of the technology applicable to the ammonia synthesis. Today I'm going to drill in very deep on the plasma chemical looping. So this is plasma application, but plasma application to microwave and to the chemical looping more complex than this. Okay, so what's the plasma catalysis? Plasma catalysis obviously means you have the you turn the reactant into plasma, then react, all right? So in the first class, remember I'm talking about the activation energy. So I keep on drawing the this. Let me go to the annotation mode. Where is my? So I'm pretty sure you see the you remember this. This is basic N2. I'm going to type here, okay? So this is EA. And then it's N2 plus H2. And then this is ammonia, okay? So you have to across the activation energy in order to react. So without catalyst, you go like this, and with the catalyst, you go like this, all right? This is catalytic, okay? Now, with the plasma, you actually different. You basically, with the plasma and catalyst, you follow this. And then you begin N2 star. That's the plasma in here. I know that's plasma in here. So basically, you elevate your reactant energy so that the distance the overcome the activation agent it drop because you pre-activate it, all right? So even with the catalyst, you don't have to climb this is the mountain peak. You just climb halfway. It's more like if you climbing the mountain. Remember the story I told you? Yeah, everybody start from the bottom of the mountain. But if you have the helicopter and lift you halfway, which is a microwave plasma situation, and then it takes less effort to cross. So this is more like helicopter take you to halfway of a mountain, then you cross. Make sense? Okay, there are two scenarios, the plasma. You can put the catalyst inside the plasma, or you can have the catalyst outside plasma. So we are going to talk about this today. The reason being that it's easy to, in terms of research, it's easy to segregate the plasma from catalyst because you can make sure the plasma generated and also the plasma landed on catalyst. Okay, so I hope you understand this cartoon. Yeah. So I'm going to come out from this this page. Let me see. Okay. Can you see my slides? You can see my slides, all right? Can you?
Yes, sir. Yes, sir. Yes, sir.
All right. So we talk about two scenarios of plasma, and then so let's talk about the next. So this is our focus because it's easy to segregate the plasma from the catalytic reaction. and this is our experimental setup. So first, we generate a plasma, and then the plasma flow onto the catalyst. Do you see the OES, optical emission spectroscopy? So this is really more like a spectroscopic technique. So you have to watch, make sure, you know, the plasma landed on the catalyst. Otherwise, if you don't have enough concentration of plasma, they may be recombined or the plasma die before they landed on the catalyst. So that means it's not plasma catalysis. So the OES, this instrument, really the key to see how the plasma is generated, how the plasma landed on the catalyst surface. It's very important because you want to see plasma chemistry rather than just a thermal heating or the microwave heating. Okay. So anyway, so this experimental setup, and then you can read this from the paper I sent to you. So I'm going to show you another way how you. I think the is in one day the audience asks question: how do you generate the nitrogen plasma? There are different ways to generate nitrogen plasma. You can put a vacuum, but you can put a vacuum, then the flow nitrogen. You can ionize the nitrogen under microwave. But that's not the way we are doing, because you don't want to put a vacuum of the microwave, because ammonia synthesis, you need some kind of the pressure. Another way is you basically produce what you call that. I think someone understand the someone mentioned about you have a microwave in your laboratory. So another way to generate plasma is more like this. So you basically you create the you begin with so you begin with argon plasma, and then you flow nitrogen onto it. Okay, so that's the way to generate plasma. You basically wait a moment. You basically you need ionize using the plasma from argon to ionize nitrogen. Is that correct? Is that what you guys are doing in the laboratory? It's called I would say it's called I think it's called the plasma argon plasma jet. All right. So you generate, then you flow the nitrogen onto it. So the whole thing will be in the reactor. You follow me? So basically by doing so, you don't have to spend too much energy on nitrogen. Nitrogen is very difficult to ionize. I think to ionize where's my cursor? N2, I think that it's 15.2 eV. So if you kick out one electron using nitrogen directly, you need to spend this much of energy, 15.2 the eV of energy to activate one nitrogen molecule. But if you have argon, you don't have to, because all those species, they basically heat N2. You don't have to spend that of energy, because the whole idea is you just need to kick out electron and then to make it ionized. Okay, I'm not going to talk about the plasma chemistry, so you can read the book. So what I'm saying that to generate plasma in this scenario, you flow nitrogen and then flow you flow argon, flow nitrogen, and once you generate, they are landed on the catalyst surface. That's the reaction we are doing. So I'm going to show you the result. Okay, so again, this is the scenario we are running. So this is more complicated than when you think. Remember, this is a chemical looping process. Okay, this chemical looping process, we treat this catalyst. First, we generate plasma. So let me.
Sir, in plasma generation, can I ask one question, sir?
Go ahead. Yeah. I encourage you guys to ask questions instead of I keep on talking. Go ahead. Let's talk. What's the question?
Sir, actually, here you mentioned with the aid of argon, we can initiate the plasma. Later on, we can combine that with the nitrogen.
Yes.
Actually, what we are facing one problem in our laboratory. Even by injecting argon, if it is more than atmospheric pressure, then it is very difficult to bring plasma.
What's the power? What's the power? The power of you you do you use you microwave? Do you use the magnetron generator or solid state generator? What's the power? How many is it? 1 kilowatt, 3 kilowatt?
1 kilowatt. 1 kilowatt.
1 kilowatt. What's the generator? Is it a magnetron or solid state?
Not magnetron, sir.
Is it solid state?
Yeah, it's solid.
Okay, so I think for the most, I have eight microwave reactors. Most of them are solid state. Okay, 1 kilowatt. So there's one I have is the what do you call that? 3 kilowatt, which is the magnetron. You probably you can generate a plasma with any microwave to sustain plasma or maintain plasma is tricky. Okay, so you probably need to go back to use the magnetron. I would say probably about 2 kilowatt the magnetron to sustain the what do you call the plasma. So that's what we use. So we use the one we generate plasma using magnetron. The machine is made by a company in France called Saran. Let me see. I don't know what you are making. So most of the instrument in United States, I think is made by half of them made by this company. I think. Is it Saran? Yeah, I think yeah. So you use the magnetron, and then I think the 3 kilowatt. So you will see the plasma. Okay. So yeah, good question. Yeah. So it's tricky to maintain plasma, but I'm talking about ambient pressure. But if you put a vacuum, anybody can generate plasma because you are dealing with such diluted the nitrogen. But if you have a lot of nitrogen to maintain or sustain you need a high power the magnetron the generator. Make sense?
Sir, yes, sir. One more question, sir. What is the reason behind the pressure influencing over generation of plasma?
Yes, because you are dealing with more molecule. You need more energy to ionize the molecule. That's the problem to maintain. So okay, very good question. Okay, let's talk about. I'm not good in plasma physics, but I can answer your question. Okay, hold on.
Yeah.
Let me answer your question. Okay, so yeah, this is okay. So this is your chamber. Okay, so I'm going to make it disappear. So this is basically your reactor chamber. So then I'm going to basically draw this molecule. Okay, let's say no. Let's do this. Okay, so N2 is N2 and N2. You have a lot of these. Okay, so all over the place. Now, when you have the N2 star, N2 star is active species, and then you have the electron, then you have electron as N, and then all kind of species. So you need energy to keep them at high energy content. They constantly ionize and recombine. Okay.
Yes.
And
yes,
recombine. So, but now you understand that constantly ionization recombine. So if you have the pressure is high, that means the chance for them statistically, they see each other is more, all right? If you have 10 molecule vacuum, they probably don't see each other. Now, under ambient pressure, you have millions of molecules. Of course, they're going to collide, recombine. So basically, it's you recombine, okay. It's ionization rate versus recombination rate. Okay, so recombination is linearly or maybe even more strongly related to the concentration, depending on how much molecule. Because when this molecule they collide each other, they just recombine, then that's the ionization disappeared. But ionization requires more power. That's why I suggest you use a high power to keep it ionized. But keep in mind, you have more molecule. They try to recombine. Okay, why they recombine? Because any particles, it doesn't matter atomic or molecular level, they try to go to lower activation state, become stable, all right? Because ionized is not stable. So the recombine is a tendency for them to go to that state. So the higher energy, they keep them in the so-called ionization state. Yeah. So that's the key. It's very difficult to run the ambient pressure. That's what, but chemical looping, that's what we run. We have to operate at ambient pressure. Make sense?
Yes, sir.
Okay.
Yeah, understand.
So yeah, just understand. Okay. So now let me interpret this one. What's the meaning of 2 minutes, 7 minutes, 15 minutes, and 30 minutes, 60 minutes? Okay. So let me interpret this to you. Okay, the first graph. Again, on y-axis is the micromole of the ammonia per gram of the agent, so which is a chemical looping agent. So to interpret this, remember this is chemical looping using the plasma. All right. So I'm going to write this. Step 1. Plasma generation, plasma flow onto catalyst, and add scope on the surface. I'm sorry, I keep on losing my cursor. Okay, here we go. It's not the catalyst. Keep onto the material and then add a soap. I'm sorry, my typing skill is not good. So that's why teaching in classroom is so easy. It's not on the surface. Okay. Not all. So material means the metal. Okay. All right. So I don't want to type in so much. Okay, that's wasting my time. So basically, step 1, plasma generation. So you generated plasma in in this region. And then step 2, and then the plasma, you want to make sure the plasma landed onto the catalyst surface, okay? And then that's I keep on using the word catalyst. It's not catalyst, it's looping agent, okay? And then you make sure adsorb, and then you follow the hydrogen. Hydrogen doesn't have to be the plasma. Keep in mind, hydrogen reaction with the metal nitride is so quick. You don't have to produce the hydrogen plasma. Hydrogen can flow, from the side onto the material. It is nitrogen coming from the top. You need to generate plasma to begin with. That's step number 1. Step number 2 is plasma flow onto the material, absorb on the surface, become metal nitride. That's a key step. And also remember the 7th step. And then someone mentioned this rate determination step. That means it's a slow step. It's really to control the whole process. Okay. The step 3 flow hydrogen and ammonia produced. So the step 2 is adsorption time. It's tricky. It depends on how long you adsorb this plasma before you flow the hydrogen onto it. So this study, the top of the curve really shows 2 minutes, 7 minutes, 15 minutes, 30 minutes. That really means, so we basically let the plasma interact with this material for 2 minutes, and then we go to step 3. 7 minutes means we run step 2 for 7 minutes adsorption, and then 5 minutes. All this time are relevant to the step 2. How long you have a plasma interact with the surface, So you can tell. Then after that, we follow hydrogen. So this bar, the height of a bar is from step 3. But each bar, the different color, is the treatment by step 2. So how long you treat it, and then in the step 3, how much the ammonia you can get. You can tell the pattern is all over the place. The reason being that, so this plasma, I would say, people use the word so-called non-equilibrium plasma, or because in this plasma region, you have all kind of species. So it doesn't mean that you treated 2 minutes, or that you treated 7 minutes, or the 15 minutes. They're not difficult to do optimization. You can, but sometimes if you treat 60 minutes long enough, it's still good, but it's the same as 2 minutes. So the point I try to make, in a short period of time of treatment, probably the plasma adsorption is good enough. If you overtreat it, probably that plasma will blow the nitride away, because the plasma, actually in this region, plasma is hot. So there are different theories behind this, but we could not interpret it. So regardless, so there's no pattern on how many in the minute you need to treat it. But regardless, the moment we have plasma adsorb, they all give ammonia. But we cannot interpret it because it's such a dynamic process. During the 2 minutes, 7 minutes, you don't know how there's no equilibrium going on, how much the plasma interact with the surface. So that's the first one. The time really means step 2, how long you treat it. But that step 2, the time really doesn't matter. So 2 minutes sometimes is good enough. Okay. So now the next curve means we basically fix the step 2 at 15 minutes. So then we run this reaction at a different temperature. That's the key. Remember this is microplasma. So this temperature is really the temperature of catalyst material here. We treat the same for 15 minutes, and then we run a different temperature. We found 200 degrees C, 250 degrees C really give it more ammonia. And then if we go to 300 degrees C, the degree 150 degrees is too low. So it looks like the optimal temperature of this material will be probably good to maintain at 100 degrees C, 250 degrees C. So this plasma, you can see how low the temperature we run this material because we have this plasma generator to begin with. If you recall, if you heat this material thermally, I'm going to go back. Do you recall this temperature? Thermally heated, you have to heat this material to 700 degrees C. And then even if you thermally heated, it doesn't subject to the equilibrium, but still you need high temperature. That's a lot of energy. And then now with in our case, and then we don't have to heat it to that temperature. So we can, I think that my computer has some problem. I keep on losing my cursor. Let's see. Okay, I'm coming back. So the specifics tell you we can maintain this at very low temperature. So this is really energy efficient. Keep in mind, this is not in the plasma zone. This is just a traditionally heated fixed bed reactor. See the wording here? It's a traditionally heated fixed bed reactor. The lower the temperature, the better, the lower the energy you spend. But then once you generate plasma, we don't have to maintain this at 700 degrees C. We can maintain this very low temperature. So this is certainly much better than the conventional heating. Conventional heating, you need to maintain 700 degrees C. So we can lower the temperature by almost 500 degrees C. 500 degrees C, that's a lot of energy savings. Make sense? Any question on this curve?
No, sir. No.
Okay, so this really this really tell you the advantage for the plasma. Once you activate the nitrogen, you do not need to run this material at high temperature. It's energy saving compared to the conventional. And then I want to refresh your memory on the microwave only without the plasma, and this material we show is better than conventional heating. All right. So there's the three scenarios: thermal, I would say thermally heated, microwave heated, and also the microwave plasma heated. So microwave heated and plasma heated, they are all better than the thermal. So this is the reason, we've been doing the research in this field, of the microwave plasma. Okay, next I'm going to show you. So we run the three different scenarios. So let me see, 2 minutes, 7 minutes. What's the hold on? I'm a little confused about this one. What's 2 minutes? So this is also step 2. Basically this will show, instead of show you the bar chart, we show you the curve. Okay, so this curve is equivalent to this, but this is just individual 2 minutes, the average. But each individual 2 minutes, 7 minutes, we basically show you time on stream how the curves look like. So if a material is treated for 2 minutes, ammonia come out very easily because this is time on stream. So that means if we pre-treated the material for 2 minutes and the plasma, and then when we flow hydrogen, you can see ammonia come out, the peak come out 5 minutes. If you treat this material for 7 minutes, and then it's a little bit delayed, it's a pink curve. If you treat this material for 15 minutes, you see this curve. So the longer you treat the material, the more delay of the material come out. The reason being that the plasma, the penetration. So if you give it too much longer time, and then there's the interaction plasma, they keep on going deeper, and when the hydrogen come in, it takes time to dissolve. Okay, so that's the interpretation of things. That's why there's no pattern for the 2 minutes or 7 minutes, how much ammonia come out. So you have to look at this from different angle, and then why they're different, because it's difficult for them to come out. That's why you don't see this amount. Because the penetration is so deep. Okay, so anyway, so this is basically from the different angle to look at the pretreatment, shorter time, longer time, but the ammonia coming out is different. The 2 minute treatment, because the plasma treated material, nitride didn't penetrate very deep in the bulk. They probably in the subsurface. That means when hydrogen come in, they dissolve. So 7 minutes, same thing. The longer you treat, the more the penetration depth and the difficult for them to come out. Okay, so this curve you have to combine with where's that 7 steps? There's 7 steps. So the longer nitrogen you treat it, the more that penetration into the bulk, right? Remember, you get the audience mentioned step 4 and 5 are redetermined step. If you penetrate so deep, and then it's difficult for them to come out, all right, as ammonia. So it's all related to this shrinking core model. So if you the plasma penetrates so deep, there's a delay to come out. So this really interpret this graph. Okay, shorter treatment time, the less penetration. The longer treatment time, the more penetration, and then there's a huge delay. So this is microwave plasma in chemical looping. Yeah, so the evolution is from the step 3, but the treatment time is from step 2. So any questions before we move on to the next? Okay, so I keep on mentioning, don't undermine this, the OES. I put it into here. OES is a very powerful tool to observe the microwave plasma. You have to make sure this is the plasma chemistry. So now I'm going to show you, when you have OES, what's the spectrum look like? So this is the OES spectrum. So there's so many peaks in there. So the OES, remember, is the optical emission spectroscopy, but with the software, you will see these peaks. So there's each peak, you can see the nitrogen, different nitrogen species. There's a nitrogen plus, nitrogen star, and a different nitrogen species. You have N2, sometimes you have N species, and also you can see the argon in here. Remember, we have argon to begin with. Now we make sure we have argon plasma, then we have nitrogen. So this is all from OES. You want to make sure you on the catalyst surface you have these peaks. If you OES pointing to the catalyst, you do not see these peaks. Sorry, your reaction is not the plasma chemistry. Your reaction is just like a microwave or thermally heated reaction. Only when you see these peaks on the surface, and then you know that's a plasma chemistry, then you can observe this is the ammonia formation, and then the desorption of ammonia at different time, and you can observe low temperature ammonia formation. It's all related to plasma chemistry. Remember, the reason you have plasma, you basically increase the so-called starting point. So they climb the activation energy curve much easier, but you have to spend energy to pre-activate the molecule. Okay. All right. So I think that we probably don't have too much time here. So I think it's good we spend the time in here. So today's day 7. I think that we talk about a lot of the Haber-Bosch is the conventional way to make the ammonia. So if you recall from the beginning, we talk about a lot of the different way to make ammonia under low pressure. Remember, so there's always the what you call the electrocatalysis, and then we spend today talk about chemical looping. Even under chemical looping, that's 3 scenario, heating scenario. And when the thermal, you should receive 3 papers. And then last two days we talk about chemical looping, thermally heated chemical looping, and also the microwave heated chemical looping. Now we just finished plasma heated chemical looping. So there are all differences. And then we also talk about there's another way, the photocatalysis, which I didn't spend too much time on it, and then plasma catalysis. Or I would say the plasma and the electrochemical. Remember, at the water surface, they have this plasma, cold plasma generated, and also they also run electrical. So there's so many scenario you can make ammonia. So I think we lectured. So tomorrow we are going to shift the gear into from the surface reaction or bulk reaction, chemical looping. We are go to the system engineer. System engineer, we have to look at the overall economics. Okay, so and then this is Haber-Bosch process on the left hand side. If you see the most of the process in the Haber-Bosch process, we are dealing with the downstream separation. It's called when the ammonia come out, they have cryogenic condenser, and then they compress and then recycle. All right, because the single pass conversion ammonia is not 100%. So you separate ammonia, you have to recycle hydrogen and nitrogen, and then you have to recondense, recompress, and move back. Now this Haber-Bosch process, since we lower the pressure and from the high pressure to ambient pressure, we do not use the high pressure cryogenic condenser. All right, because if your reaction is ambient pressure, why you have to use high pressure the condenser? There's no brain, because it's not necessary. So tomorrow I'm going to lecture the different method of the ammonia at absorption connected to the low pressure operation. If you see this is the downstream of not Haber-Bosch reactor. We are not using Haber-Bosch. We are using the microwave or electrochemical reactor. And then what's the option of the downstream separation? The downstream separation has to be associated with the ammonia reactor. If ammonia is low pressure, so you have to look for something else. Tomorrow we are going to talk about thermal swing and also the chemical absorption and also some other mechanism. Okay, so to produce ammonia not necessarily used for the as ammonia as a fertilizer. However, if you really use ammonia, if you know for sure I'm producing ammonia as a fertilizer, the easiest way will be if you talk to farmers.
Sir,
okay, go ahead. What's the question?
Sir, before we discussed about the kinetics, that activation energy for the reaction. Activation energy is decreased by introducing chemical looping as well as plasma catalysis or microwave catalysis concept. Once you introduce plasma catalysis or microwave catalysis or chemical looping, you can minimize the activation energy. In the sense, the reaction can achieve with the least activation energy. So how we can evaluate, in what way we can order it, sir? Which one is obtaining least activation energy, and then incremental.
Very good. The system engineer will tell that if you do the system engineer, so you have to basically run a simulation. So very good question. You save energy on the reactor side, but you have to consider how much energy you put it in. Okay. Very good question. All right. So let me start from the very good question. So now I'm going to draw so this is a Haber-Bosch process. So this is, don't look at the right hand side. Right hand side electrochemical. So on the left hand side is the Haber-Bosch process. So I'm going to basically spend time on this. Okay. So let me give you if you do the so-called system engineer, so look at the whole process. Okay. So let me give you very good question. Yeah, I think that the cursor keep on losing my cursor. Okay, hold on. Can you see this blank slide? Okay. Energy.
That way.
Price yeah, I don't know. I don't know.
Okay, so basically, if you look at this the cartoon, okay, so basically the if you look at the count on the energy the span on this direction, it's really like this. So feedstock pretreatment in the Haber-Bosch process, you feedstock pretreatment just preheating. Okay, so typically in Haber-Bosch process, preheating is a heat exchanger because the reactor release a lot of heat. You do the heat exchanging and then you preheat it. Okay, so that's the Haber-Bosch process. And then reaction. So reaction means how much energy you put in the reactor and then downstream separation. Okay, so that's a so very good question. Tomorrow you will see the economic analysis. We actually break down the energy spent on this reaction pretreatment. Now in the Haber-Bosch process, so we don't spend too much in the reaction and in the feedstock pretreatment, and then downstream the separation is loud. So let me write it down here. So for the Haber-Bosch, I would say this is the average energy, average E. And then if you look at the reaction, I would say average energy. Okay, energy means E. Okay, I'm going to break down the energy span. Okay, for Haber-Bosch, downstream separation very high. Make sense? So keep in mind, feedstock pretreatment, reaction, downstream span very high. Okay, I would say it's very difficult to write on here. HB process. Make sense? Now, okay, let's see the password. Okay, now I'm from so obviously your question is, so we spend the energy to pre-treat feedstock, not just preheating, we turn in the plasma, all right? So that means feedstock pretreatment high, all right? You agree? Reaction, I can say probably very high. Very high. Makes sense? Because you have to elevate the energy. What about the reaction? Very low, all right? Remember Haber-Bosch is 500 degrees C. Remember how much the temperature we have? 200, all right? We only need 200. Follow me? So that's energy saving, okay? So now, so that's why tomorrow we need to talk about economic. So remember we lower the pressure, all right? We lower pressure, that means you don't have to use the cryogenic, you don't have to use a compression, high pressure compressor. Make sense? You see what break down from very high, because you do spend, I mean, nothing's free, okay? So you spend the energy on feedstock pretreatment, you save energy on the reaction, now you save energy downstream. So tomorrow we are going to focus on downstream because we cannot use a traditional Haber-Bosch compressor. So in the day one, if you remember, okay, this is clear, all right? This energy breakdown, you will see the technical economic analysis, we have pie chart, and then how we save the energy. Okay, does this make sense? Haber-Bosch, average feedstock treatment, average the energy reaction, but the very high the downstream separation. But we have very low, about very high, very low, very low. Follow me? Make sense?
Yes, sir.
Okay.
But in microwave plasma, downstream separation is itself very low. Is it possible, sir? Actually, downstream side, yesterday we discussed a few things. One is with nitrogen, another one is without nitrogen. I mean, nitrogen mixed with ammonia, then nitrogen is incompressible. Difficult to segregate nitrogen and ammonia. If hydrogen is mixed with ammonia, then we can easily segregate. Or water vapor is mixed with ammonia, then we can easily segregate, like we mentioned yesterday. So downstream separation, you mentioned very low for microwave plasma.
Yeah, because by the way, microwave plasma, that's a process. Downstream separation, you do not use the plasma anymore because you are using the adsorption technology. It's not, downstream separation has nothing to do with the microwave plasma. Microwave plasma just enable low pressure operation so that you don't have to use high pressure cryogenic. Downstream separation is just simple. You can use the conventional, the low pressure adsorption. You follow me?
Yes, sir. Yes, sir.
Okay, so let me write it down. I think if you write it down, you can you know what I'm saying. You know what I'm saying. Okay, so
downstream separation.
Downstream. Okay, sep means separation. I want to save time. Okay, separation. HB. You have to use high pressure cryogenic. You agreed, all right? That's your only option. Do you understand what I'm saying? Exactly, downstream separation for HB process, you have to use a high pressure cryogenic. Now, lower the system pressure. There are many options of low pressure separation. Make sense?
Yes, sir. Understand, sir.
Yeah, so that's the same thing because all the commercial price, you heard about the pressure swing, all right? Pressure swing or the membrane, you cannot use membrane for the Haber-Bosch because today's membrane will not tolerate very low temperature cryogenic condition because membrane, some membrane, they are polymers. You cannot freeze membrane, put in the Haber-Bosch. You cannot put so much pressure on membrane. So they are not even option. So Haber-Bosch only option will be cryogenic. Now, when you lower the pressure using plasma, you downstream separation, you can adopt so many commercial process. That's the key. Microwave plasma, lower the pressure, leave you a lot of options. That's energy saving. Okay. So how expensive? Remember in the first class, how expensive cryogenic? Let me go back here.
Now I got it.
You know what I'm saying, all right? This condenser, high pressure condenser, all this the compression for recycle is a 3-stage. If you want to compress anything from ambient pressure to the 300 bar, you need a 3 compressor. Okay, it's not the 1. You have to go 3 stage, 1, 2, and 3. That's why it's just, yeah, I know we are running out of time, but I want to make a point. Okay, so let me, before you guys go, I want to show you something very quick. Hold on. So this the things. Oh gosh, I will talk about tomorrow. I think every time I change to annotation, I'm running out of my space. So basically, if you look at my cursor, and then this section, look at my 6th section.
Yeah. Yes, sir.
It costs you a lot of money. If anything fail in this section, which I covered, and then you had to shut down the plant. but any other location failed because they have redundancy. They can afford the the A and B. Remember I say you have pump A on running, you have pump B on standby. This is whatever in this circle, you don't have option because they are so expensive and such the customer made. You don't, any of these three equipment goes down, you have to shut down whole plant. But now we are not running Haber bars, simple low pressure. There's so many options here. So that's the flexibility of the unconventional, either called microwave chemical looping or thermochemical looping or the microwave plasma chemical looping. So that because the low pressure give you many options. Okay, so I'm going to stop here. We are running on 2 minutes out of time. So tomorrow there will be the downstream separation and followed by the technical economic. And also we are going to do tomorrow there will be 3 lectures. One of lectures, I want to give you guys maybe 20 minutes time to read the paper and then do a quick exercise before you go. Read this, not this one. So read this paper, the first paper. Where's that chemical engineering technology? So I'm going to highlight here. It's in one of the paper Dr. Anand sent you. Go back and read that paper. I want you to do a exercise to calculate if you come up with the same conclusion. Okay, read that paper, and this is what I cited from the paper. So they need 1.2 ton metric ton for manganese, and then to produce 100 kg ammonia per day. All the data are in our paper, so you don't have to spend too much time. Just read some of the key data, see if you come up with the same thing. So tomorrow we are going to spend this going to be case study, and then it all help you how you size the reactor, chemical looping reactor. So we are going to spend one lecture talk about this reactor sizing, followed by adsorption technique, low temperature, low pressure, and the technical economic. So that'll be tomorrow. Okay. So depending on if we can finish. Thank you, everyone. See you tomorrow.
Yes, sir. Thanks for the nice doubt clarification, sir. Now I got a clear idea about this and downstream part. I'm very happy and have a nice day, sir. Thank you.
Okay.
Yeah.
Thank you.
Thank
you.
We will share the links.
Yeah, please read our paper. Okay, so the by the Peter From. So so then I think that will be the case tomorrow. The arrangement will be case study. So I want to show you how you do I would say the very simple, quick calculation, so you can size the reactor chemical looping because you need 2 reactors running back and forth. So the amount of material and also size the reactor is a cost. Okay, all right. Again, see you tomorrow. Yeah.